Hey, today we're going to look at diffraction and interference, two phenomena that display the wave nature of light. So diffraction is this phenomenon where, if you look at the animation here, you have these flat waves that come in and hit a barrier. This yellow piece is a place that blocks the wave. And there's a little opening in this barricade where some of the waves are allowed to travel through. And as you see, when they go through this tiny opening, they go from being flat waves to being these circular shaped waves. This really goes back to Huygens' principle. It states that each point on a wavefront is a source of circular waves. And when the parts of the wave are blocked, the circular pattern is revealed. So what Huygens is saying is you really have these flat waves, but they aren't really flat waves. They're really a bunch of circular waves on top of each other. But because of the way that they interfere with each other, the way they superimpose, you end up just seeing the flat wave that travels towards here. And as soon as you remove parts of that wave, you start to see this circular nature of each point on this wave. Now, the idea of diffraction itself is not very important or interesting to us, but it leads us to the next phenomenon. So as you can see on this slide, we have what's called an interference pattern. And the interference pattern shown in this animation here is really a consequence or a result of this flat wave coming in. And now instead of just going through one opening, it's actually going through two openings. And you can see the result of that is now we have two semicircular waves coming through. And you start to see, if you're not hypnotized by this pattern of places where if the white lines represent crests of waves, you can watch these crests, and there's certain points where these crests kind of run along with each other. So you'll notice, I'll highlight one here. There is one right here. If you kind of watch along this yellow line I'm drawing, the waves just kind of travel along there. If you watch, there's always two crests running into each other, and then they'll move towards the right side of the page. There's another location, you can see it right here. If I draw it carefully and just follow one of these things, yeah, you can see if I follow along these two crests, I get another line where there'd be these places where these crests are meeting each other and making, if you'll recall, when two crests meet, they make a larger crest. We can see another location on this side. All I have to do is find a place where they intersect and then follow it along with my pen. And you'll see another line of intersection points, this other place where crests are meeting crests. We can follow along. That's not the end of the story. You can continue out here and you can see another one. You can go out here and see another one. We have this pattern referred to as an interference pattern. So strictly speaking, when two circular waves interact, the crests and troughs will produce an interference pattern, this pattern of superimposed crests and troughs. So while our eye is probably trained, if we look on the center one here, our eye is probably trained on what's going on with the crests. The same thing is happening with the troughs that are in behind them. So every point here where there's a crest meeting a crest and moving towards the right, you can look between the points where the two white lines intersect, and you'll see two dark lines are intersecting our two crests. So not only along this line are we getting huge crests, we're also getting huge troughs. So this is a location where there'd be a lot of disturbance of the wave in the water. Now, interesting thing is, if you go in between, I'll just draw this one more time to highlight it. If you go in between these points, like this line that I'll draw in blue along here, if you kind of follow along here, you'll see, if you take enough time to watch for it, you'll see that this is a line that no matter where you look, there is always a white line right on top of a trough. In other words, a crest from one of these sources is meeting a trough from the other one. And if you'll recall, when a crest meets a trough, you get this cancellation of the waves, or you get this place where there'd be no waves going on. So we get flat, if this was water, flat water here, huge rippling water here. Here's a video of what you would see if you could see these water waves. And like I was saying, you can see these points where there's huge crests and troughs that ripple out in this direction here. I'll highlight those in yellow. So here's an example of a place where if you put your rubber ducky on the water here, you're getting hit with lots of huge crests followed by huge trough. The surf is good there. On the other hand, there's also this location such as this one right here, where there's really very little movement of the water, and that's because crests are meeting troughs and they're canceling each other out. If we look at a still shot of the interference pattern, it looks like this. We have two sources, source 1 and source 2 indicated here, and then you can see the crests and troughs that are generated at each source kind of frozen in time for us. And if you trace and look at some given points, for example, anywhere along this solid line here, you'll see that a crest from source 1 right here is meeting a crest from source, the crest from source 2 there is meeting the crest from source 1 here. So there's a place where you get a huge crest because of those two crests meeting. And that happens all along this line. On the other hand, if you look along the dotted line, you'll see that this dotted line highlights everywhere where a crest meets a trough. So I'll just put dots everywhere there's a crest, and you'll see that right underneath, it's a trough. And so a crest, for example, I'll highlight this one right here, this crest from source number 1 right here is meeting a trough. I'll highlight it with a dotted line right here that's coming from source number 2. So these regions of huge crests and troughs, the dark lines, and no crests and troughs, so very little movement of the water, are indicated by the solid lines and dotted lines. Now, turns out you can reproduce this interference pattern not just in water, but also, or with mechanical waves, but also with light waves. When you perform this experiment with light, you would not necessarily see all of these lines in here. You wouldn't see anything in between here. But if you put a screen at a location, a distance away from your sources, you get these alternating sections of bright and dark lines. The bright points being places where crest meets crest, making huge crests, troughs meet troughs, making huge troughs, and that moves towards the screen and eventually hits it here. So we see a bright spot here, a region where the light that we use would be very bright. On the other hand, there'll be regions in between where the crest from one source meets the trough from the other and makes this dark line. So the interference pattern for light shows up, unlike water waves that we can see on the medium, we don't see it until we project it onto a screen and see these regions of bright spots, dark spots, bright spots, dark spots. Now, the fact that this is a pattern lends itself to be analyzed mathematically. So here's the first of two equations that we will use to analyze the interference pattern. And it's got a few different names. We'll refer to it as the interference pattern to start with. So this is interference pattern equation number 1. And it says this, that lambda, or wavelength, is equal to d sine theta over n. So we'll go over the nuts and bolts of this, and then we'll revisit our picture and talk about each of these elements. So in this equation, lambda, or wavelength, lambda represents wavelength in meters. D in our equation is the distance between the slits. So we'll go back to the picture in a moment and revisit that idea. Theta is the angle, but more specifically, it's the angle between the central, what we call antinode, the central region where we got these huge crests and troughs, and whichever nodal line or antinodal line, not to discriminate, being studied. And n is the number of the antinode being studied. We really should talk about antinodes to start with. So let's revisit the picture for a moment and make sure that we understand how each of these variables show up in that picture. All right, so now we can see our equation, our variables, and our picture all at one time. So lambda, well, that's the wavelength, and that would be the distance between crest to crest on a wave. So that kind of gets established back here, but at any time we can talk about the wavelength And it's the same no matter which opening the wave goes through. Once the wavelength has been established back here, then that's the same wavelength in all locations. So that's our lambda. D is the distance between the slits. So on this diagram, I think it's fairly clear, there's a opening right here, there's an opening right here, and the distance between these two things from here to here is the D. So that's our D, the distance between the slits. That would be measured in units of meters as well if we chose that. Theta, that's the angle between the central antinode. So this is a special bright spot right here, this middle one. So we refer to that quite often. That's the central antinode. And so the angle between the central antinode and the node or antinode that we are studying, that is the angle referred to as theta. So this would be theta that I've identified here between the central and the first antinode. We call that maybe theta 1. If we wanted to measure to the second one, we could do that. We would just measure from the central one all the way to maybe this one here. We could measure that, and we get a different measurement, about twice the original one, no surprise. By the way, this is a very symmetrical situation. So whatever we measure from the central maximum to one side will be the same as what we would measure to the other side. So it doesn't matter which side we choose. Finally, n is the number of the antinodes. So what happens in these situations is we start with the central antinode being n equal to 0, and then from there we count outwards. So this would be n equal to 1. That's the first bright spot that we see on the wall. This would be the second one, so we call this n equal to 2. And again, which side you choose to study doesn't really matter. It's symmetrical, so that would be n2 as well. That would be n1. This would be n2. So we just count outward from the central one. If we count the minimums, there's going to be a few terms that we're going to get to in a moment, but if we count in between these bright spots, we get these centers of these dark spots. I like to tell students, and that's the note down here, count this as 0.5, and then this one would be the n equal to 1.5. In terms of our equation, it works really good. So when solving for what we call nodal or dark spots, we use the 0.5s. So the attitude with n is really start with the central one is 0, and then count your way outward, half, 1, 1.5, 2. So that's the formula and kind of the qualitative business of the interference pattern equation. There's a lot of little details we got to be careful of, and so I'm going to kind of get to that before we get into solving a single problem. And one is this idea of how do we create this situation with light, and the way that we create this phenomenon with light is to use something called a diffraction grating. And diffraction gratings really act as double slits for light. You have to appreciate that if we're sending a water wave through an opening and we want to see it diffract and interfere, then we need simply to kind of make a barrier out of bricks or something like that in the water. We could do that pretty easily. And then as the water waves travel towards this, we can visually see this. But if you consider what's going on when we're dealing with light, the wavelengths are so extremely tiny that this whole apparatus has to be extremely tiny. And to pull that off pretty easily, we use something called a diffraction grating. So you'll hear reference to this. But really, they just act as double slits. The problem is often on a diffraction grating like the one that I have pictured down here, they don't tell you the D, they actually tell you the line density. So check it out. This one actually has 3 different line densities. So there's 3 diffraction gratings for the price of one down here. And they tell you that one of them is 100 lines per millimeter, one's 300 lines per millimeter, and one is 600 lines per millimeter. So we have to have a way when we're given that information to convert it to the D, which is what we want. Because this is not D, this is, you know, not a measurement of a distance or anything like that. And so I'll cut right to the chase for you. If you want to find D, D is always equal to 1 over the line density. no formula for this, but it makes some sense that if we know, for example, in this case, that we have something with 100 lines per millimeter, so 100 lines in 1 millimeter, then we just inverse that thing. There will be 1 millimeter cut into 1,000 lines, if you want to think of it. And that's literally what this diffraction grating is a bunch of lines on this grating. And this one would just have more lines per millimeter, and this one would have even more lines per millimeter. It's just putting a bunch of these things in here that in the end behave like double slits. For our purposes, we can convert between line density, lines per millimeter or lines per meter, whatever it happens to be, and we can say, oh, this is 0.01 millimeters between the lines. The D is 0.01 millimeters. So be prepared. Sometimes you're given D, sometimes you're given the line density. You just need to roll with it no matter which one you get. Now, probably already slipped a couple of times talking about this thing, but there's a bunch of different ways that people will refer to the experiment itself, this double slit interference pattern phenomenon. And there's a lot of ways that we talk about the pattern itself. For example, if you think about what's going on, when we produce the interference pattern, if we have our diffraction grating right here, and we send some light towards it from maybe a laser beam or something like that, we get these this pattern on the wall. So we shine, let's say, laser light here. We'll get a pattern on the wall where there's a bright spot right there. Then there's a bright spot on either side. This is what it kind of looks like. So we sometimes call these bright lines, these points here. They're also sometimes called constructive interference, which kind of makes sense if you think about it. We're making huge crests out of two smaller crests, so they constructively interfere. You're actually going to see them called antinodal lines as well, these regions where there's huge disturbances. So all these things are the same. And a throwback to the original experiment back in the day when people were probably still somewhat speaking Latin in science classes, this was referred to, the bright spot was the maxima. This is where light was at its maximum. So all these things are really the same, different ways of saying the same thing. We're talking about this region where there's a bright spot on the wall. We're getting huge crests and troughs accumulating. On the other hand, you also have this other locations where you get these dark spots, these dark lines, dark spots. These are sometimes called destructive interference because crest is meeting trough and canceling out. And they're sometimes called nodal lines. They're these lines where there's nodes or no movement. And of course, if we got our maxima, we must have our minima. So bright spot, dark spot, bright spot, dark spot. Introduce these terms to you because depending on where the questions come from and who's describing it, whether they're talking about a certain experiment or another one, you might hear any combination of these things. Finally, the whole scenario I've been referring to as an interference pattern, it really comes about because of an experiment sometimes referred to as the double slit experiment or Thomas Young's experiment because he was the original person that did it. But like I say, these are just all synonymous terms. So just become comfortable with the different terminology, how we can refer to the bright spots, dark spots, and this whole experiment all around. Okay, now maybe we're ready to tackle a problem. Just a warm up here. So we're talking about light, so blue light. Blue light has a wavelength of about 460 nanometers. So in this question, we're going to use blue light with a wavelength of 460 nanometers. It's incident on two slits that are 0.55 millimeters apart. So all my talk about this line density doesn't matter here. They're telling us the distance between the slits. And they want to know what's the angle of diffraction for the third antinodal line. So pay attention to this. A lot of people will focus on this third and they'll say, oh, that's n equal to 3. But don't forget, it could be, we could be talking about a screen where we see the central antinode, then the first one. So if there's n equal to 0, n equal to 1. Often people will number the nodal lines want the first, the second, and the third. So you got to be careful. They don't call this n equal to 0.5. Mathematically, that's what it is. But in questions, and if you did this in real life, you would probably count this as the first dark spot, then the second dark spot, then the third dark spot along the wall. So yeah, getting back to this, it is an antinodal line, so this is a bright spot, so that's good. This is, our n. All right, so summarizing what we kind of have here, we have n equal to 3. We have the wavelength of the blue light, it's 460 nanometers. We're going to have to, we'll write it as 460 nanometers right now, but we'll change it quickly. And then our d, the distance between the slits, is 0.55 millimeters. So I know the formula that we're going to use here to find the angle is that wavelength is equal to d sine theta over n. And I'm looking for the theta. And so everything looks good. I got my d, my n, and my lambda. I just have to make sure that I work in the same units. You don't necessarily have to put everything into meters because, as you'll see, when we multiply and divide out, all the units eventually will cancel. And if we're solving for an angle, we'll get it. So you're free to kind of put your distance measurements, all your length measurements like wavelength, like distance, and things like that. You're free to put them in the same units, but they have to be the same. So in this case, it's just easier. I happen to know, and you'll get familiar with this too, that a nano is the equivalent of times 10 to the minus 9. So to me, the easiest way to put this into meters is just literally put 460 times 10 to the minus 9 meters. And I know that it takes 1,000 millimeters to make a meter, so this would be like move the decimal 3 places, so this is 0.00, yeah, 0.55 meters. So in terms of information that we are given, we have our wavelength now in meters, we have our d in meters, so when we're done, these units work well together, and they should cancel out and allow us to solve for the angle. So let's put it into the equation and see what we get. 460, and again, I just tell you, if it's up to me, I would just literally put it into my calculator this way. I mean, if you really want to show off your scientific notation and write this as 4.6 times 10 to the minus 7, good for you. But if you want to avoid any too much conversion and too much moving from scientific notation, and just go ahead and write that as exactly what a nano is, 10 to the minus 9. D, 0.00055 meters, the sine of the angle, and divide by n. N is 3. We put that into our calculator. You'll get two numbers. First of all, the sine of the angle, and I'll give you a word of warning. You end up dealing with some pretty small angles with things like this. So the first thing I got was when I rearranged and solved for the sine of the angle, I got 0.0025 something or other. And then when I take the inverse sine to find the angle, I only get 0.14 degrees is my angle. 2 significant digits because of the d. Again, get used to it. Sometimes the angles are pretty small, and that's just the nature of these kinds of questions and the interference pattern when you do it with light. So in the end, you have really a few ideas going on here. We have the idea of diffraction, which leads to this interference pattern. And the interference pattern we understand qualitatively to be the interaction of two circular waves coming from two separate sources that interact with each other to produce this pattern of huge crescent troughs and sometimes no crescent troughs, but it's a pattern that we can mathematically analyze. And the first equation that we're going to use is this one that says wavelength is d sine theta over n. All right, Good luck. Try out a couple of questions with this equation and see how it goes. Just sometimes the devil's in the details, so be careful about the idea of D versus line density. Keep track of your units. Make sure you're always working in the same units, even though you could, like I say, it's up to you if you want to work with millimeters, centimeters, meters, but be consistent. Once you pick one, go with it.